All right. Hi, everyone. Hope everybody is doing well and safe. In this video, I want to go over correlation and regression. So basically, we're going to talk about linear correlation in this lecture. What's a linear correlation? First of all, when you talk about correlation, you are dealing with a bivariate data. That means you have x's and you have y's, and the goal is to know if there is a linear correlation between these two variables. What can be a linear correlation? For example, if I say studying hours and test scores, you want to know if more hours somebody studies gets better test scores. So you want to know if there's a linear correlation between studying hours and test scores. So for that, you can pick a sample, ask the students how many hours you study and what was your test scores, and come up with the scatter plot. So X can be the hours of studying and Y can be the test scores. So then you can find out if there is a linear correlation or not. Now, how does the calculation work? First thing you wanna know is R. R is called the linear correlation coefficient, and that's the formula for R. This is a long formula, but the calculator or the technology can do that for you. So what is R? R is a number between 0 and 1. So each time you calculate R and you get greater than 1 or less than 0, a negative number, that means you are doing something wrong. So please be careful, especially if you do hand calculations. Now, if just looking at it, if R is almost equal to 1, then you can say there's a positive linear correlation. That means the slope of the line is positive. If R is almost equal to -1, then there's a negative linear correlation. That means the line is going to go down. If R equals to 0, or almost equals to 0, then there is no linear correlation. So here, in this case, for the first graph here, so you see there, we can say there is a positive, the line, if I try best fitted line here in between points, it has a positive slope. So here R is almost equal to 1. Second case, R is almost equal to -1. Third case, no linear correlation, so R is almost equal to 0. And the next interesting case is here to look at. There is a correlation, but that correlation is not linear because it's not a straight line. So again, in this lecture, we're going to be dealing only with linear correlation. Now, there is, to make sure that there's a linear correlation, you can refer to this table for R values. So critical values of the Pearson correlation coefficient R. That's also called, R is also called Pearson correlation coefficient. So you look at your sample size. For example, sample size is 8. And there are two significance levels. We're going to just use this. If the significance level is not given, just use 0.05 always. So 8, you get the critical value 0.707. You put the positive number here for the critical value and negative 0.707, for example, here. If you're linear, then you calculate R. If R is after the positive critical value, then there's a positive linear correlation basically in this region. If it's before the negative critical value, then there's a negative linear correlation. R falls here. And if R falls between these two numbers, you say no linear correlation. I put another note here. I want you to be careful from now on. Causation is not correlation. And people misuse that all the time. And they say some variables causes a change in some other variable. For example, if I say, we hear that all the time, smoking causes lung cancer. smoking does not cause lung cancer. The right way of saying this, there is a correlation between smoking and lung cancer, but smoking doesn't cause lung cancer. If smoking caused lung cancer, then every single smoker would catch a lung cancer. So, and from now on, if somebody talks about causation, be careful, listen to that, and then see if it's causation or correlation. And most of the time, is correlation, and people you say that it's causation. Now let's go over this introduction. Linear correlation and regression analysis. We start with establishing linear correlation for bivariate data, x and y. So we know what bi is 2. So we're dealing with two variables here. You can draw the scatter plot, the first thing. Then you can calculate R, check to see if there's a linear correlation or not. Once you do that, then you can come up with the equation of this line. So you can find the equation of that line. Now we know from algebra the equation of a line is given by this formula, y equals to mx plus b, where m is the slope and b is the y-intercept. So in case of regression or linear correlation, you can call that's also called y hat, which is ax plus ba and m are exactly the same thing. There's an example here. Draw a scatter diagram from the following data of 9 randomly selected supermodels' heights and weights. So heights are the x values and weights are the y values, and we want to know if there's a linear correlation between height and weight of supermodel. So x-axis, you can put your x values, and y-axis you can put your y values, and then that's the scatter plot, and that's exactly the same thing. So let's read this. Since the points are fairly close to each other, we expect a fairly high degree of correlation between the given bivariate data set. Further, since the points reveal an upward trend from left to right, the correlation is positive. Hence, we may expect a reasonably good degree of positive correlation between the given bivariate data. Let's see if that's true. So next step, you have to calculate R. And again, that's formula, we saw that on the top. And there is the hand calculations here. So let's see, in this formula, we need sum of x's, sum of y's, sum of x's squared, sum of y squared, and x times y. So you write x's and you write y's here, square each x, and you get that. We need the sum, so the sum is here. Square each y and write it here. So the sum is here, and x times y is that number plus that number. Each time you can write them here and add them. And once that's done, so these are the values we see. You can substitute all of them in this formula, and if you do that, the R is 0.814. Again, so you can see that 1, 2, I use both of them because some books they use capital R and some books they use lowercase r. Now let's see. Here, in case this is close to 1, but then just to make sure, you can go to the table. If you go to the table, n is 9 because they check 9 supermodels. So the critical value for 0.05, and again, use 0.05 if the alpha is not given. If they say 0.01, then you take this one. So the critical value is 0.666. So again, 0.666 positive here, negative 0.666 here. Then you compare the value of R. R is to the right of 0.666. It's 0.814, so there is a positive linear correlation. Now the regression. Linear regression is the study of the model equation that describe the relation between the bivariate data. This equation is known as the line of best fit or regression line. We will also use regression equation to make predictions, very important, and construct the prediction intervals. Well, we won't do that in this lecture, but we can come up with this line. In algebra, we know the equation of a line is mx plus b, where m is the slope and b is the y-intercept. You can calculate those values by using these formulas. M is n times sum of x by minus sum of x times sum of y over n times x squared minus sum of x quantity squared. If you go back to the table, you have all these values. So you can substitute them, and if you do that for m, you get 3.626. And the formula for b is given right here. Can you have all those values? If you substitute, you get negative 133.238. So the equation of that line is given. For our study, we can call that's for the sample. So y hat equals to 3.626x minus 133.238. Now this is the equation of this line. So you know that you can have a best fitted line next to these points. So what's good about that? You can predict. So forecasting or prediction. Now we can use the regression equation to predict a y value known as y hat for a given x value known as x0. If I say predict the weight of a supermodel that is 69 inches tall, so you know x or x0 is 69. What you bring the formula in for x, you put 69, then you can predict the weight, so which is 116.97. Very important note here, if there is no linear correlation, that means you do all these calculations and your R falls here, there's no linear correlation. If the question or the problem asks you for the best predicted value, in that case, the best predicted value is going to be y bar. Y bar is the mean of the y values. That means sum of y divided by n. So one more time, if there is no linear correlation, the best predicted value will be y bar. Do not use the line or the equation of the line, because that's not going to be the best prediction. Now, if we calculate if we use this formula and we calculate the y hat, which are the predicted values, so, and for each one of them, these are the observed ones. And if we use the equation of the line and we calculate, we get all these values. And a residual is y minus y hat, that number minus that number. So you just want to see for the observed one what the residuals are. So basically these are, if this is the equation of our line, these are the residuals, y minus y hat. In this case, the residual is going to be a positive number, and in this case the residual is going to be a negative number. So you can calculate all that, residuals, and you can plot the residual. The x values stay the same. So we have the x values, which are the heights. For each height, you draw the residual. So then you get this scatter plot. But how do you analyze that? So you want to see by the residual, you want to see if this is a good linear model or not a good linear model. So here I showed some examples. If all those points when you draw the residual plot are close to the line and spread with no pattern, just like this first one, this is a good model. Sometimes you're going to see a pattern like a curvy residual plot. When you see that, that's not a good model because there's a pattern. And sometimes here you see the lines that points are close to the line, but they get far away from that. So if that happens, then you say that's not a good model. Now the calculator, I do want to show you the calculator. The steps, I have it here. So again, if you use the TI-84, you go to stat, edit, put x's in L1, y's in L2, then go back to stat, go to calc, and pick number 4, which is linear regression AX plus B. Then once you pick that, enter that, you go so frequency list, you don't do anything and just go you for the regression equation. Actually, this should be so go to regression equation, then you can say vars, go to vars, y vars, pick number 1 function, and then pick number 1 again, y1, and you can say calculate. Make sure when you do this, the diagnostic is on. How do you turn on the diagnostic? You go to second function 0 catalog, scroll down to diagnostic on, and enter a couple of times until the diagnostic is on. But let me just go over this. These are the notes. I will show you how this works. So let me share my calculator screen, and we're going to go over the same example by using so again, if you want to do that, you go to stat, edit, enter that, and in L1, don't worry about L3 and L4 right now. In L1, you put the X values. So here the heights, and in L2 the Y values. Then you go to stat again, calc, and scroll down to linear regression, and you have X list is L1, Y list is L2, frequency list, do not worry about that. And let me just say calculate. I'm going to come back to that. I want you to notice something. Here we have the linear regression, or the regression, the equation of a regression leg. And as we saw, we have our A, the slope, and the y-intercept. So that's given. But I don't have R or R squared. So how you can see R and R squared, we have to turn on the diagnostic. So you go to second function, 0 catalog, and you just scroll down. You can go directly to that, but just go until you find diagnostic on. You enter that a couple of times so it's done. Now if you go to stat, calc, and number 4, and let's just say calculate or enter, the calculator will give you R squared. I'll talk about that in another video, and R, which is 0.814, and we found that by hand calculations. I showed it to you. Now let's see if we can draw the scatter plot with the equation of the line. So we go to Stat, Calc again, Enter, and you come here where it says Store Regression Equation. I'm going to do this very slowly. So you go vars, then you pick y vars and enter that. So it's the function and pick y1 and you should see y1 here. Now if you calculate this, nothing will change. You get the same values. But now we can do the scatter plot with the line. So in order to do that, again, you go to second function, stat plot, which is on top of y equals to. Pick the first plot, enter that. Make sure it's on. Then the type of graph is just this first one, the scatter plot. Make sure X values are L1 in L1 and Y values in L1, L2. And so once you enter, that's where you pick the graph. To see the graph, you do zoom 9. And we see our graph. So with the scatter plot with the equation of the line. Now, if you go to trace, you can easily read those values here. So it's going to give you. Now I want to do the residual. To draw the residual by using your calculator, same thing. You go to the second function, stat plot, enter number 1. We already had it. And you come to y. We need to change our y list to the residual. Here, once you do that, you have to go to your list. So you go second function, list. And if you scroll down, the calculator will have that for you. Number 8, it says resid. So enter that. Now instead of y list, we have the residuals and do the same thing. And you can do zoom 9. And there we go. It's the residual path. You want to read those values, just trace. So, and you can read them. Okay, let me stop sharing this. I think that's it. That might have been a long lecture, but please watch it 2-3 times, especially the last part with the calculator, and try to repeat what I did by using your own calculator. And once you do 2-3 times, it becomes pretty easy and straightforward. I think that's it for this lecture. Stay well and safe, and I'll see you soon. Have a good one, everyone. Bye-bye.